Okay, so today we start second topic about about computer hardware. So it will be about interfaces. So probably you know or you use some interfaces. So the most popular is USB, but in computers there are more interfaces which are commonly used, even the user doesn't know about it. So before I start talking about particular interface, I'd like to make introduction about how digital data are sent. So there are several methods which are used in modern interfaces. So I'd like you to know what is the difference or what particular terms to mean. Yeah. So okay. So first, I'd like to start from talking about line coding method. So assuming that we have a stream of bits, so zeros and ones, and we want to send it from one point to another point, so we have to encode it. Yeah? So we have to create a digital signal which represents 0 or 1. So the simplest way, okay, is to use a voltage signal. So where V plus represents 1 and low voltage level is 0 or minus V. So the V is the signal amplitude, so the power supply voltage. Yeah. Okay. So in this point we have encoders, so it creates or transforms a string of bits into the voltage signal, and here we have decoder which does it opposite. Yeah. So there are several simple methods which let us to do it, but sometimes we transform not only a single bit, but we convert a group of bits. So we have 2 bits for example. So we have, in this case, we have 4 different, let's say, symbols or tags, and we represent it using voltage signal or using different voltages. So every of this group has different voltage level assigned. It may be done. Okay, so the way how we represent a group or a single bit depends on something which is called line coding. So what are the aims of line coding? So first aim is to adjust the way of transmission to physical properties. So for example, for optic fiber, the line coding will be different than for metal wire. Yeah. So it depends on the medium. The second very important topic is synchronization. So sometimes the line coding purpose is not only to send a string of bits, but to ensure synchronization. I will tell something about synchronization in a moment. The third is balancing. So for some medium, it is important or there is a requirement of signal balancing. So it means that the average value in certain period of time should be 0. So there shouldn't be, DC component in signal. Why it is so important? Because if we have DC component in signal, for example, in wire, the current flows, and we don't know it. We don't want it. No? It may generate, for example, some magnetic effects we want to avoid, and so on. The fourth purpose of line coding may be a data compression. I will show you some examples where we can achieve data compression when we transmit. Okay, so I think that the most important issue related to line coding is synchronization. So we have two possibilities. So now I'd like to explain what is synchronization, or what are the effects of lack of synchronization. So look, here we have a transmitter. So transmitter transmits bits using voltage coding. So we have plus V and minus V levels. And here we have a receiver. So the electrical scheme is like this. So here we have transmission line, and on the other side we have the receiver, so transmitter receiver, which try to recognize the sequence which was sent. So look, if here in this situation we assume that every bit, so duration of every bit is constant. So let's say it takes delta t. So delta t is a duration of particular bit. But transmitter has its own clock, and the receiver also it has its own clock. So it's obvious that there are no two identical clock sources. So in case of transmitter, the duration of delta t may be longer than in case of receiver, or opposite. Yeah, it's so. Of course, here we have exaggerated example, but I think it's important to understand it. So for our receiver, delta t is like this. So it takes less time than for transmitter. So what may happen here? Okay, here instead of recording a single bit, receiver may distinguish or record that there are 2 bits of 1. Yeah? Then we have 0. Again, we have 3 bits of value 1 instead of 1 bit of value 1, and so on. Okay, this example seems to be exaggerated, but in fact, it may happen. So let's assume that we want to send data. So the duration of particular bit is, okay, transfer rate is 100 megabits per second. So comparing to serial ATA or NVMe, okay, it's not so huge because serial ATA has about 600 megabytes, NVMe even more. Yeah, so we have 100 megabytes per second. So the duration of particular bit is 1 times 10 to minus 8 second. Yeah, so this is the duration. So look, if this duration is so short, the effect of desynchronization, so different speed of clock in transmitter and receiver, may be evident. So let's assume that the difference in speed is, let's say, 1 nano second. So it is equal to 1 times 10 to minus 9 of second. So you can see that it is 10 times smaller than duration of particular bit. And we want to assess how often we can observe errors. So look, if we send a signal which takes 10 times so we send 10 times 1 and we send it by transmitter. So if we have the difference like this between transmitter and the receiver will count not 10 but 11 bits. So additional bit will be added. Of course, it is also true for when there are different values. Yeah, but you can see that, okay, sometimes for some bits they will be recognized properly, others not. What is the problem? Okay, if we add additional bit here and we send binary data, everything will be moved. So not only this bit will be falsified, but here this bit will be interpreted as the value on this position. So other values will be also interpreted on the wrong way. So it moves everything one position right. Yeah. So you should be conscious that the falsification of particular bit in transmission generates problems for other for further sequence also. Yeah. So this is very problematic. Okay, so how we can cope with lack of synchronization? Of course, we can use line coding, yeah? So or proper line coding. So there are several line coding methods. I'd like to briefly mention about some of them and tell you something about how synchronization can be achieved. So the first or one of the most commonly used method was NRZ, so no return to zero coding. So this method works like I told you that the voltage, every bit is coded using a particular value. So we have high value for bit equal to 1 and low voltage for bit equal to 0. But what about synchronization? For interfaces like that, the synchronization can be achieved on several on a way that the receiver synchronize on the edge. So when we have we have change of the level, so the level changes from 0, for example, from 1 to 0. Okay, so it changes here. We know that a new bit starts. So the receiver may reset its counter and start counting from this point. So I showed you here that if we don't have synchronization, okay, the problem will occur every, let's say, every 10 bits. No? If we have 1 nanosecond lag. But if we apply synchronization on edge, you can see that, okay, here a particular bit was found, but here, because the edge is changed, I can synchronize my counter, so 0 will start here, in this position. So, okay, if it would not be so exaggerated, and the error was every, let's say, 10 bits, we can observe that if we have a sequence which consists of different, okay, if the sequence consists of bits of the same value, one extra bit will be added. But if the sequence consists of different bits, okay, let's say here is 11001100. So in this case, even there is a difference in time base between transmitter and the receiver, this error will be compensated using edge. So if the edge occurs, the receiver changes or reset its counter, so it starts counting from this point. So now it is able to, properly distinguish between bits. Of course, if we increase transmission speed, the effect may be like this. So to make synchronization in this scheme, we need at least one level change per period in which the error may occur. So if we know or estimate that the synchronization is 1 millisecond and the bit duration is, let's say, 1 nanosecond and the bit duration is 10 nanoseconds, we require a 1 bit change per 100 nanoseconds. If not, okay, errors will be generated. Okay, so the second method is an RZ, so no return to zero code. So you can see that, okay, non-return to zero inverted. It is used in, for example, in USB 1 and 2. So you can see that here the change of signal is related to the bit. So for 1, the change occurs, and for 0 not. So look, if we have stream of bits of value 1, for every bit, so if we have 1 here, for this bit, the signal change will be observed. If there is 0, nothing will happen. But if there is 1, the signal will be changed. If 0, the state is not changed. Okay, so this is another way how we can code data. What is the difference? If we have string of the same values and these bits are 1, every single bit can be distinguished. So it's improved synchronization. But if we have a stream of bits where there is constant 0, okay, there is a lack of synchronization. Another method, which is not so popular, it's called a return to bias. So how it works? 1 is denoted as an impulse. So we start from bias. There is a high level, and it returns to bias in a single bit duration. So what is the problem here? Okay, we have synchronization for 1s. So every bit of value 1 is perfectly synchronized because I can distinguish it, yeah, because I observed 2 level changes per bit. But the problem is that we have to generate 2 level changes per single bit. So in this case, we have, if I'd like to transfer data with speed 2 megahertz, I have to ensure that the transmitter should be able to drive a transmission line not 2 megahertz but 4 megahertz speed. So in general, it is ineffective method because in this case, I would be able to transmit the data of a speed on speed of 4 megabits using, for example, the protocol like this. Here, the synchronization on ones would be better, but for zeros, there are still lack of synchronization. Here you have return to zero coding. So you can see that this return to bias, I have two levels of voltage, V plus and V minus, and both for 1 and for 0, the return to bias policy is applied. So as I told you, this method is quite difficult because I need two different voltages. Moreover, the transmitter has to drive line twice time faster than the transmission speed is, so it may generate problems, it increase costs, and even we have self-synchronization, so we can synchronize every bit, so we can extract it, so there are no risks that additional bit will be added. This method seems to be not effective. Okay, I think that it's not so important. In IR controllers, so the controllers you use in TV sets or for other devices, the signal is transmitted digital using pulse width modulation. So every one, so it's similar to Morse alphabet, yeah. So the duration of 1 and duration of 0 is different, but for every bit we have 2 level changes per bit. So one is encoded like this, so we can distinguish it using duration of this phase. Yeah? Okay, so now we start talking about more complex channel coding methods, which were commonly used. So the first of them is multi-level coding. So it is denoted as 4B 3T, so 4 binary 3 ternary. But in general, this method may be extended in different levels. Okay, so how it works? In this method, we have 3 levels of voltage. So, for example, we have -1, 0, and +1. So it doesn't matter what the voltage is, but we have 3 different voltages accessible. Data is splitted into packets or groups of 4 bits. So for 4 bits, we have 16 different combination. And these 4 bits are coded by using 3 line bits. So look, here I have data bits. So this is the first group. And in line coding, this value is converted on signal which looks like this. So the signal changes from -V, then +V, then 0. This group is coded different. So I have plus V, minus V, and so on. So look, every 4 bits are coded using at max 3 level changes in signal. So we have less level changes in signal, but we have to have more voltages here. So look, I have 3 line bits, 3 levels, so it gives me 27 different combinations. So I have more combinations than the number of groups I have to encode. So therefore, we have different, larger number of combination. I can reject line bits which are equal to 0 or constant equal to V plus or constantly equal to V minus. So in this case, I can ensure that the level change will be observed at least 1 time per 3 bits. No? So for every packet here, at least 1 level change will be observed. So this ensures me that I can apply a self-synchronization. So even the receiver and transmitter base time may be slightly different. Every 3 bits, the transmitter will be able to synchronize. So this is very important feature. The second feature is that because we have 3 line bits instead of 4 bits of data, I can achieve a compression. Because the compression is for 4 to 3 times. So this method can be applied for in different combinations. So, for example, I can have more voltages levels or different size of channel bits and so on. This method was also used in Ethernet 1 gigabit. Okay, it's not applied in our computers because in our computers it works different, but there was a version of Ethernet using this method. So look, in this case, we had 5 levels, voltage levels, and 4 lines coding. So we had 4 lines in which data were sent. So in this case, every bit was, so we had 256 different combinations of levels on these 4 lines. So in fact, we were able to send the data on a speed which is 8 times lower than the speed of the interface. So every line worked at speed 250 megabits per second. And I think it should be even less. So it should be not 250, but 128 megabits per second. So look, we have the transmitter which operates on lower speed, but the transmission throughput was 1 gigabit. So here you have an example how a single byte, because we have 8 bits which are encoded using a single channel bit. So for 4 lines, we get different voltage levels here, and they were, so single byte was sent as a single channel bit in this interface. Okay, here you have different methods, which is, commonly used in current interfaces like serial ATA, NVMe, HDMI, and so on. So most modern interfaces use this method I'd like to mention now. So this method is called a block coding. It is usually defined as XB over YB coding. And now I'd like to tell you something about this method. So again, similar to PAM coding, we have a stream of data is divided into groups. So we have group of M data bits or X data bits, and this group is substituted by Y channel bits. The difference between PAM coding and block coding is that usually these blocks are, or channel bits, there are more channel bits than data bits. So we don't have compression. So the number of bits is in transmission line is a little bit higher, but it gives us a certain benefits. So some benefits. So how line coding works? Here you have example 5B over 6B code. So it means that we send a block of 5 data bits, and it is encoded using 6 channel bits. So it means 6 level changes in our interface. So what can be seen here? We have input. So here you have all combinations of data bits. And here you have 6 channel bits, which are substituted when particular combination will be is encoded. So look, for some combinations, we can you can see that we have 2 possibilities. So now I'd like to tell you something about this. So what is the benefit here? So look, in this line code values, you can see that there are no values where the number of the same bits or subsequent bits of the same value is higher than 3. So here you can see that we can achieve self-synchronization at least every 3 bits. So in this case, we can send data on higher speed. Why we have different values for some for some entries? Because look, if we want to ensure self-synchronization, the value is selected based on the previous value. So, for example, if previous value was 1111 here, to achieve self-synchronization, this option will be used. If the last bit was 0, okay, this option will be used. Okay? So depending on the previous values the proper elements will be selected. Using this method, we can also achieve error detection, because if transmitter receives data which are not in agree with this pattern, so for example, this sequence was decoded and then it, oh, maybe not. Okay, so let's say this sequence was decoded and now transmitter receives this value. Okay, it's 000, but based on the encoding policy, it knows that it should be 01000. So it detects that something was wrong, so it may prompt the user or inform that, you know, data is corrupted. Okay, so this method adds only a single or several bits for line code, and we achieve a self-synchronization which works better than NRZ or other line coding methods. Look, therefore, this method is used in different interfaces like Ethernet, like PCI Express, like Ethernet 10 gigabits. So we have, of course, different blocks of data. So in PCI Express, we have 8B over 10B. In Ethernet, we have 64 bits, which are coded using 66 bits. But you can see that it gives us a real, so this block coding generates a real progress in interfaces. So before time it was introduced, the serial interfaces, so interfaces where data are transmitted, you know, using a single lane, were limited. So using this method, we are able to achieve a frequency higher than 1 gigahertz. Okay, so maybe a short break. So I'd like to tell you that the first, let's say, digital interface was something which is called a Morse code. Hope some of you know this method, but probably you don't know why particular character representation was used. So in Morse alphabet, every character is represented using a set of dots and dashes. It was developed for telegraph communication. So there was a serial interface where the sender, human sender, generates a sequence of long and short and long pulses. So why E, for example, consists of a single dot, I consists of 2 dots, and so on. T is a single dash, N is dash and dot, and so on. So the Mr. Morse, who invented this this code, analyzed fonts in print house. So it turned that some of them were he analyzed the frequency of font replacement. So it was correlated with the frequency on which particular font was used. So therefore, it turns that in English language, E is the most commonly used character. The second one was T. Then we have E, I, A, and M, yeah, and so on. So based on this method, it assigned particular, characters. So it assigned particular symbols to the characters. So the time of sending E is the shortest because, okay, it occurred the most often. So using this method, he aimed to minimize the time of sending messages, yeah, using Morse code. Of course, it is applicable for English. For example, for Polish, okay, probably there is a different configuration for there would be a different configuration for characters, but okay, we use it in every language. Okay, so now I'd like to tell you about more, maybe not about something which is quite difficult to understand, but it is very important method of maybe not line coding, but of increasing interface or wireless interface speed. So first we start from, math. So I don't know whether you have on your math classes Fourier transform or Laplace transform, but I'd like to tell you about Fourier transform, only graphically. So look, probably some of you which have, amplituner or other device like this, you have something which is called equalizer. So equalizer led us to, when we hear music or listen music, or so equalizer led us to set different gains for different frequencies. So in this case, we can, boost basses, or we can boost higher frequency, depending on your preferences. So in fact, the equalizer calculates something which is called a Fourier transform. So it calculates the representation of the signal which is transmitted in different coordinate system, where on x-axis is frequency and on y-axis is amplitude for particular frequency. So look, here we have a sinusoidal signal, and this signal can be converted or transformed into Fourier, into spectral, by using Fourier transform. So in this case, if we have pure sinus signal, we will see a single bar here. So this signal is transformed to this representation. So in spectrum, we can observe only a single mode for frequency f0, and its amplitude or power will be dependent on amplitude of the signal. So there are several basic operations or relationship between a signal which is recorded in time with the image we get in spectrum after Fourier transform. So the Fourier transform of two mixed signal. So we have two signals. We sum them in time. So we mix them. Yeah, is equal to separate Fourier transform of every of them. So if here we have two signals which we can sum up, we will observe the separate spectrum for every of this signal. And the second feature is that when we multiply two signal in time domain, so in time, the resulted spectrum will be something which is called convolution of their spectrums. So now I'd like to show you how does it work in practice, and then I will tell you how it was used to improve interface performance. So look, let's assume that we have this red line denotes a signal, and this green line denotes something which is called a carrier wave. If we analyze the spectrum of signal, it may look like this. The carrier wave is sinusoidal signal, so there will be only a single bar for the carrier wave frequency. And now, if we perform signal modulation, so we multiply our signal by carrier wave, we get signal which looks like this. So here you can see the envelope, which shape is taken from the original signal. But what happened when we calculate Fourier transform of this modulated signal? We will see that this spectrum was shifted in a place where the carrier wave was observed. So this effect is called convolution. Okay, so let's try to use it. So let's assume that we have different signals, but every of the signal is modulated using different frequency. So we have signal x1, x2 up to xn, and every of the signals is modulated using different frequency. So in spectrum, we will see that the spectrum of particular signal was shifted in frequency domain. So when we sum them up, so we have to add the signals in time domain, and we calculate the Fourier transform, you will see that all of the signals can be distinguished in frequency domain. So if I can send them using a single, let's say, medium, even single layer, wire, or wirelessly. And you can see that if I cut this part from the signal, I can recover the original X1 signal. The same, if I demodulate this signal, I can recover X2 signal and so on. So even the signals were mixed together because they were modulated using different frequency. I can extract every of them. Okay, what would happen if there would be no modulation? So try to imagine the situation where several people start talking at the same time. So everything will be mixed. So there will be no way to, extract or separate every of them. So this method is used quite commonly used, especially in wireless transmission. So let's start from, radio. Yeah, if we have, I don't know which is your favorite radio station, but you know that the every station has something which is called a frequency assigned. So let's say that we have the radio station 96.7 megahertz. The other radio station may have, let's say, 102 megahertz. I don't know what are this radio station, but it doesn't matter. So, of course, average human is able to hear information or sounds in a range from, let's say, 20 up to 20 hertz to 20 kilohertz. So we can see that it is definitely higher frequency than we are able to hear. But what is going on? If we have, in fact, this is modulation frequency. So the voice of so if we have 96.7, okay. So coming to this slide, having a radio station, so every radio station has its own frequency, so let's say 96.7 megahertz. So the voice is modulated with this frequency. And for another radio station, there is another modulation frequency, and the voice or sound is modulated with this frequency. So if you set your receiver or your radio on particular frequency, in fact, it performs demodulation of this band. So it is taken, demodulated, and then it is sent to your speakers, so you are able to hear it. So this method can be also applied to wireless transfer of data. So look, in this case, I have several channels, and in these channels, the independent data streams are sent. But every stream is modulated with different frequency, so there is a different carrier wave frequency. And after modulation, it is summed up and transmitted. On the receiver side, the modulation is performed, so this process is opposite. So the particular band is extracted and carrier wave is erased. So it led me to recover also the n independent streams of data. In fact, for digital transmission, the modulation looks a little bit different. So we don't use amplitude modulation, but mostly the phase modulation is used. So how phase modulation works? So we have carrier wave, and depending on bit value, when particular bit is started, the phase of the signal is changed. Using phase shift keying, we can apply it to modulate not only single bits, but also groups. So for example, 8PSK, which is quite popular method, apply the phase shift to signal depending on value of a group of 3 bits. So for example, having 111, it generates a phase shift by 90 degrees. If we have 110, it shift phase by 45 degrees. So every change will generate a shift of the signal by particular angle, let's say. So in this case, so this process is used in Firewire, in Wi-Fi, in Bluetooth, in ADSL. So you can see that in most wireless transmission method. Not only wireless, yeah, because ADSL is not wireless. But this method can be used also for optic fiber transfer. So when we have optic fibers, in fact, we have two kinds of fibers. So we have single mode fiber. So in this fiber, we are able to send only a one wavelength, but we have also a multi-mode fibers. So in these fibers, we can send waves of different length, so different colors of signal. So in this case, I can, using different colors, so different, carrier wave, I can encode different data stream. So on receiver side, so this signal is mixed, but that when we use, for example, prismatic device, we can easily split this signal onto different or separate components. So even it is mixed inside the optic fiber, it can be easily extracted. So every channel can be easily extracted. So in fact, so here is called, this effect is called a division multiplexing. So you can see that this effect can be used in many applications, both wireless or optic fibers. In fact, I don't know, probably you don't remember this time, but maybe some of you. This effect was, I think, one of the most crucial factors which led to improve the internet connection in, yeah, I think in 2000 years. So up to this time, when I use a telephone line to connect to internet, everything was blocked. So when I used a modem, nobody could call or make calls and so on. When ADSL technology was introduced, nothing was changed. So still there was the same telephone line. But in fact, the telephone line utilized only 4 kilohertz of the frequency to send voice. The farther part of frequency were unused. And in ADSL technology, this farther band of frequency was used to send data. So it was divided into channels, and in every channel, the independent data stream was, modulated and sent. So using this technology, we were able to achieve, let's say, 5 or 6 megabits per second of transfer. And at the same time, we could make telephone calls. So I think it was a really breakthrough technology, of course, for this time, yeah. But yeah. Okay, so now I'd like to change a level. So I'd like to tell you something about methods of digital data transmission. So far, I told you about line coding, about how we can multiply the stream of data by using modulation. Now I'd like to go real low level. So I'd like to tell you something about some physical aspects. So in general, we can divide the digital data transmission methods into two groups: wire links and wireless links. Of course, we have also optic fibers, but okay, let's focus on this two. So if we have wire link, we have several options to send a single channel bit. So we can use something which is called a voltage signaling, a differential voltage signaling, a current modulation, and current signaling. So let's try to focus what are the differences between them. So if we have voltage signaling, I have single transmission line, and here I have a ground level. So data are transmitted and received with respect to something which is called a ground. So the common potential. But what may happen if external electromagnetic interference induce or will induce a disturbance here? So look, I can have a stream of bits here, and now if the interference is generated, it may induce an extra bit. So extra depression, or it may induce or depress the value of the particular signal. So it may falsify it. So in this case, a new bit will be, observed. So the style, and it is very typical for voltage interfaces because the input impedance of receiver is high. So we send data, and there is only a low current required to send data using this method. So the second, on the other side, we have interfaces which are use current signal or current loop. So they work like this. I have two lines, and every line is terminated. So I have resistor. It has 100 ohms. And on this side, I have also resistor of 100 ohms. And then here I have transmitter, and here I have receiver. So if transmitter generate a voltage signal here, the current flows. So if current flow, you can see that if the potential is 5 volts, the current which flow is about, here the impedance is, resistance is 60 ohms. So let's say that it's less than 100 milliamps. It's a huge amount of current, yeah? So, so in this case, even there is interference, it is not able to induce the current of 100 milliamps. So these interfaces are less prone to disturbances. So they are used, so these interfaces are CAN. It is commonly used in automotive applications. So in most of cars, everything is connected via CAN, like ABS, lights, security systems, audio, and so on. So, and the second interface is RS485. But the problem is that the huge current is supplied here. So this interface is not power safe. Okay, the trade-off between voltage signaling and current signaling are the differential interfaces. So how they work? I have two lines, and I have transmitter and receiver. But here I have line A and B, and when I send signal, so here is signal on line A and here on B. So when I send signal on line A, I send signal which looks like this, but on line B it is opposite. Of course, this is simplified, so there are some certain differences, but I'd like you to understand what is differential voltage signaling. In fact, so when we have a receiver, it subtract the signals. So in fact, when I subtract B from A, I will get signal of which has 2 times higher amplitude. But what happened if the external interference is observed? So usually these wires are twisted. So they goes next to each other. So we can expect that the induced potential will be similar in both of these wires. So let's assume that a voltage or extra voltage was induced here and here. So if on the receiver side, if signals are subtracted, this will be subtracted too. So in this case, the differential voltage signaling is able to remove interferences like this. Of course, regarding the robustness for interference, the most prone are voltage signaling. But differential voltage signaling is more prone for interference than current signaling, but it consumes less power. So therefore, this method is commonly used in current interfaces like USB, serial ATA, PCI, and so on. Okay, I told you something about synchronization. So here you have an example where receiver clock is 0.1% faster than sender clock.
Sorry.
Yeah.
There's only one thing. I think we have a quiz in 2 minutes, or like 1 minute now.
Okay, sorry, yes, of course. So, okay, so we stop this lecture. So thank you for your attention. Please switch to quiz and goodbye.